Welcome to the session. In this session, we are going to cover the orientation tolerances. Under orientation tolerances, we have three geometric characteristics. They are perpendicularity, angularity, and parallelism. This is the second category of the tolerances, orientation. After the form tolerance, now we are going to see the orientation tolerance, the second letter O in the for PL. Orientation tolerances control the relationship of a part feature to one or more datums. So the main point which we are going to find difference from the form tolerances is we need a datum reference in this case for orientation, because we are going to orient the part with respect to some datum. So they specify how far the part feature can vary with respect to the datum. So with respect to one particular datum, the corresponding part feature can vary according to the geometric tolerances. How much is the distance it can vary? To explain those things, we need a datum. So that is what orientation tolerance is defined. Now we are going to see the perpendicularity tolerance. So perpendicularity can be applied to features of size as well as for plane surfaces also. So they need a datum reference always. In the feature control frame, now we will be using the third category also, third zone also we will be using. In the form tolerances, for all the form tolerance we don't have the datum reference, but for the orientation tolerance we need the datum reference. Based on the application, a perpendicularity tolerance zone may be cylindrical and perpendicular to a datum plane. So in this example, you can see here the tolerance zone defined is a cylindrical geometric tolerance zone and it is perpendicular to a datum plane. So that is what it says. So in this figure, you can see the axis of the actual component should be having a perpendicularity tolerance of 0.2 millimeter. That is a cylindrical tolerance zone with respect to a datum plane, because perpendicularity is a orientation feature. So you are going to orient one feature with respect to another feature. So the other feature will become the datum plane. So definitely we need a datum in this case. And it may be a distance between two parallel planes perpendicular to a datum plane. So what it is trying to say is, you can see the two blue color plane. These are the two control zone, the perpendicularity tolerance control zone, and they are called as the two parallel planes separated by the distance of the tolerance, that is the perpendicularity tolerance, and these two are perpendicular to the datum plane with respect to what it is going to here. So in this feature, you can see there are two elements, you can say horizontal element and vertical element. So in this case, what we are trying to define is the vertical element should be within this much tolerance zone perpendicular to the horizontal zone. So in this case, the horizontal features datum plane is at the bottom. With respect to this datum plane, how much your vertical feature can vary from the perfect 90 degree. So perfect 90 degree, that is what it says, the perpendicularity tolerance here. So it is the distance between the two parallel planes separated by the tolerance value given for the perpendicularity. The perpendicularity tolerance means the entire indicated surface must lie within a specified wide tolerance zone that is perpendicular to the datum plane. So in this diagram, you can see the two parallel planes are created, separated by a distance, that is separated by 0.004 as per this particular feature control frame, and they are perpendicular to the datum feature. So in this case, the datum is A, that is the bottom profile is the datum. With respect to the bottom profile, how far from the 90 degree your vertical feature can vary. So this distance is 0.004. So this is what this drawing explains here. In this diagram, you can see here the slot. The slot is given here. The slot should have a perpendicularity tolerance of 0.005 with respect to the datum plane A. So datum plane is here. The datum plane A is here. With respect to this datum plane, the slot should be perpendicular. So means it should be separated by a distance of 0.005 between two parallel planes. So these two parallel planes will be parallel to the future which we are defining, but it will be perpendicular to the datum always. So that is very, very important. So the perpendicularity tolerance means that the center plane of the slot must lie within a wide tolerance of 0.005 that is perpendicular to the datum plane. So these two reference planes are perpendicular to the datum plane. So this is what perpendicularity tolerance means. So here it is applied to a whole feature. So what it is trying to say here is perpendicularity should be within a wide tolerance zone of 0.1 with reference to datum A. In this case, datum A is the top surface, and you have the whole axis. The axis of the whole should be having a perpendicularity tolerance. So we have created two features. So we have created two reference planes, and these two reference planes are separated by a distance of 0.1, and center axis of your hole should be lying between these two planes. So these two planes are perpendicular to the datum A. So these two are the main important points we need to consider. So the plane which we are taking into consideration for the tolerance control should be perpendicular to the datum which is represented in the feature control frame. Application of the MMC for perpendicularity. So when we are applying maximum material condition for perpendicularity, what will happen? So in this case, we have a pin. So this face is made as datum, and the pin smaller diameter is 8 mm, and it is having a tolerance of plus or minus 0.005, and as per the feature control frame, it says the perpendicularity tolerance should be within 0.003 cylindrical tolerance zone at maximum material condition with respect to A. So when this pin diameter is at maximum material condition, the perpendicularity between this pin and this face should be within a cylindrical tolerance zone of 0.003 with respect to datum A. So that's what with respect to this datum A. So the maximum material condition of the pin, since pin is a male feature, the maximum material condition will be the maximum diameter, that is 8.005. So the pin can vary between 7.995 to 8.005. So when the pin is at maximum material condition, you don't have any additional tolerance, and it should strictly lie within the tolerance value, the perpendicularity tolerance value which is given in the feature control frame, that is 0.003. So now we will take an example. In case we have produced a pin which is having a diameter of 8.001, then as per this chart, the bonus tolerance will be 0.004. As maximum material condition is 8.005, your bonus tolerance becomes 0.004, and as per the drawing, you have the tolerance value, perpendicularity tolerance value as 0.003. So now you have a room of 0.004 bonus tolerance plus perpendicularity tolerance 0.003. So this pin at the size of 8.001 when it is produced can be having a perpendicularity tolerance up to 0.007. So if your component, after checking that the diameter is 8.001 and the perpendicularity is lying at around say 0.005, it is accepted. If the perpendicularity tolerance is at 0.007, it is accepted. When it goes beyond 0.007, it is rejected, provided your material of the pin diameter is 8.001. So now how we are going to measure perpendicularity? So perpendicularity of a surface can be checked with an angle plate and a dial indicator. So we will use an angle plate to clamp the component which we are going to test it out, and this angle plate set will be kept on the surface table, and then we will use a dial gauge to dial it out on the surface which we are going to measure, and based on the readings provided from the dial indicator, we can find out the values. So I will show you a few clips now so that you can understand how the perpendicularity can be measured. So if you look into this video, they are going to check the perpendicularity with respect to the bottom face towards the vertical rod with respect to the bottom diameter. So for this, they are going to keep this component on the V block. They will attach it to the V block and keep it on the surface plate. So V block is, as you know, it is going to be a 0,0 face. So it will be placed on that one, and it is locked using the magnet so that it will not get disturbed. And now they will use a dial gauge to dial the surface. So now when they are going to dial the surface of the pin, so it will give how much perpendicularity it is with respect to the bottom face of your component. So based on the indication shown in the dial gauge, the perpendicularity tolerance can be calculated. Since it is applied over the entire surface, see, at one point they will keep, and they will keep it at the peak point. They will try to catch the peak point, and they can make it as 0, and it can be moved on the surface. can see. So it will be moved over the surface, the other end. So they are going to touch at the other end, and based on the deviation, how much they are going to get, that will show the perpendicularity. So this video shows the perpendicularity here. So you can see the perpendicularity with respect to this face and the horizontal cylinder, horizontal shaft. So this is kept on a V block, and this component will be rotated. So they have a stopper pin here so that it will be perfectly straight, and according to the deviation occurred, so face perpendicularity from here to here. So we checked, the previous slide was showing like it was checking, it was clamped, the bottom face was clamped and the pin diameter OD, the surface was checked. Now the pin OD is being rested out and they are checking on the face. So based on the dial indication, we can calculate the perpendicularity. So representation of perpendicularity in a drawing. Now how we are going to represent the perpendicularity tolerance in the drawing. You can see the feature control frame here. So it is completely filled now. Until the previous sessions we were seeing only the first two slots were filled, first two zones were filled. Now we have coming to the orientation tolerance, so we have the third zone also. So the symbol for perpendicularity is a perpendicularity. This is the symbol. So one horizontal line and one vertical line. So one horizontal line at the bottom, above which a vertical line is placed. This is the symbol for perpendicularity, and it is having a tolerance zone shape as well and tolerance zone size as well. So here tolerance zone shape is not compulsory. If it is having a cylindrical tolerance zone, you can apply, otherwise it will be blank. When it is blank, it says it's going to be a wide tolerance zone, not a cylindrical tolerance zone. And the material condition also applies, that is the tolerance modifier, maximum material condition or least material condition is also applied. If required, you can apply. And the third one, datum reference. This is compulsory, and this datum reference you can apply with modifier also. The maximum material condition can be applied for the datum also. Suppose you have a pin diameter as a datum, then the diameter can have maximum material condition as well as the minimum material condition. So you can apply tolerance modifier to the datum reference as well. So to a typical representation of perpendicularity symbol using the feature control frame will look like this. So as per this one, what we can read is the feature for which this feature control frame is attached should have a perpendicularity tolerance at 0.005 when it is at maximum material condition. That too, it is a cylindrical tolerance zone. Cylindrical tolerance zone of 0.005 at maximum material condition with respect to datum A when the feature datum A is at maximum material condition. Now we will see the next topic, angularity. This is the second orientation tolerance which we are going to see now. Angularity symbol is an angle, an acute angle, say 30 degree, something like that we can put. So that is the angularity symbol. Angularity refers to a part surface, center plane or axis at a specified angle other than 90 degree to a datum plane. It is almost similar to that of the perpendicularity, but only difference is perpendicularity is mentioned for the surfaces when they are at 90 degree, and whatever the angles other than 90 degree, they all come under the category angularity. If you have two components assembled at an angle of 30 degree, 40 degree, 45 degree, 60 degree, everything will be considered as the angularity tolerance. You can see in the drawing, so the angle between these two profiles, these two features are at 30 degrees. So other than 90 degrees applied. So here you can see angularity is indicated with respect to 0.1 tolerance zone and with reference to a datum A. The angular dimension is always a basic. So normally angular dimension will be basic. So the tolerance for the angular value will be derived from the feature control frame. Depending on the application, an angularity tolerance zone may be distance between two parallel planes at a specified base angle from a datum plane or axis, or a distance between two parallel straight lines from a datum plane or an axis. So in this drawing you can see the main thing is this particular feature which is selected at a 60 degree they are showing. Two parallel planes are created and the value is 0.03. So the distance between the two parallel planes is 0.03, and this particular feature which you have selected, the surface, should be lying in between these two distance. So the datum is at the bottom. With respect to datum A, what is the angle? So other than 90 degree, you can specify here. So in this figure, the angularity means what it says is the feature which we have selected. The feature is a hole. The hole's axis should lie within a wide tolerance zone of 0.2 at an angle 45 degree with respect to datum A. So here the datum A is the bottom feature. The angle between the datum A and the axis of this inclined hole should be lying within a wide tolerance zone. The distance between the two parallel planes which we have selected for controlling should be within a distance of 0.2 wide tolerance zone. So your hole can be lying anywhere in between. The whole axis can be lying anywhere in between these two planes. So that is what it is shown in this figure. So two parallel planes they have created, and this axis of your hole can vary from here to here. So the distance between these two is 0.2. So again, one more figure to explain this. So the angularity tolerance means in this case, the entire selected surface should be lying within a tolerance zone of 0.005 with respect to datum A. So at an angle of 30 degree they have created. So this full surface, you can see here, the waviness surface should be within these two parallel planes which are separated at a distance of 0.005. With respect to the bottom plane datum A, it should be within a tolerance of 0.005. So how we are going to check angularity? Normally inspection of angularity is done by using a sign plate or sign bar and with a dial indicator. So what is mean by sign bar? A sign bar is a device, so it is like you can use this one and you can adjust your angle accordingly. So how we are calculating is we are using the slip gauges here. You can use a lot of slip gauges according to the height you can use here. You can see sin theta is equal to opposite side by hypotenuse. So that is the formula which we have studied. So this length we know how much it will be standard center to center distance of the sign bar, and this is the height which we need to calculate. So by using this sin theta, you know, if your component's angle is say 40 degree, using the 40 degree value you can calculate the height, how much it should be. So according to the height you need to select the slip gauges and use the slip gauges to that much height, and you need to keep the sign bar on it and keep the component above the sign bar. Now what will happen is the surface that has to be measured will become straight, that is parallel to the surface plate. Now when we use a dial gauge and we dial it over the surface plate, it will show how much variation it is having with respect to the parallel plane. Now what we are trying to do here is the angle 40 degree angle of the feature which we need to measure is made as parallel to the surface plate, and we are dialing it out. If it is having some taper, so it will show in the dial gauge. According to the variation you can adjust your slip gauge height also and make sure that it is coming 0, and based on the new height which you are going to achieve, you can put the value and you can calculate, you will get the new angle. So instead of 40, how much it is, 40 degree and 5 minutes or 6 minutes, so it will show you. I will show you a video so that you can understand how the angularity is measured. So in this case what they are trying to do is they are going to make this one parallel to the surface plate. So this is the surface which they are going to measure it out. This is the control surface. So this is a detailed video. You can see how the operator is going to use the sign bar and how he is going to set it out. So this is the sign bar, and the black color one is the component. This is the sign bar, and these are the slip gauges. So he is going to take a new slip gauge because the variation was more. He will use that one. Again lift the sign bar and place the sign bar on the new height which he has achieved using the slip gauges. And now he's trying to make this surface again parallel, and he's going to dial it out. So he will be doing the same thing repeatedly until he makes sure that this top surface is showing 0 deflection using the dial gauge. You can see the dial gauge value now, it is 0. See how much it is going to show the deflection for him when he is moving. Yes, from -22 it is showing lot. It's going up to 20. So then again he says, oh, it's not okay, it's not showing 0. Again he need to add few more slip gauges according to the height, according to increase the height. So he is taking some slip gauge and he is replacing with a suitable size of slip gauges as per the deviation again. So slip gauges are nothing but blocks of standard calibrated thickness. So they will have a standard thickness that will be regularly calibrated and made sure that it's not having any deviations, so that the whatever height you are measuring, it will be perfect. So again he has used the new slip gauges and he is putting the sign bar once again on the slip gauge, and he is trying to make sure that the surface is showing 0. Again he will dial and he will ensure it is showing 0. So until it makes 0, so you can't do any calculation. So we need to make it is showing 0. When it is at 0, we need to calculate how much is the slip gauge's thickness we have added, and using that we can calculate the angle. See, now it is perfectly okay. The dial indicator is showing no deviations. So the height, what is the total height now he has used, he will use it for the calculation of the angle. So this is the method of checking angularity. So representation of angularity in a drawing. So how we are going to represent the angularity in a drawing using the feature control frame. So the feature control frame, you can see it has 3 zones again. So you have the angularity symbol and acute angle line like this, it's drawn, and tolerance size is there. It doesn't have a shape, it's not cylindrical, it's always a distance, so wide tolerance zone. So the diameter symbol will not be there, and you can apply the modifier, tolerance modifier, you can apply like material condition, maximum material and least material condition, and a datum reference is definitely required, compulsorily it is required. And again you can apply the tolerance modifier for the datum reference also, it is possible. So this feature control frame, how we can read is the feature for which it is attached should be at an angularity tolerance of 0.005, a wide angularity tolerance of 0.005 when it is at maximum material condition with respect to datum A when datum A is at maximum material condition. Now we will see the next topic is parallelism. This is the last geometric characteristic in the orientation tolerance. So parallelism symbol is represented by a two parallel, like a angled line, like a slanting line, two lines separated by a small distance. So parallelism refers to a surface or center plane that is equal distance at all points from a datum plane. So how we can understand this one is, a datum is given here, datum A is given. The distance between the datum A and the surface you are going to select, it should be at equal distance whenever you are selecting at any point. So this is the surface which we need to select, and this is the datum. From here to this distance, from here to this distance, from here to this distance, the vertical distance, everything should be same. So that is the within the tolerance zone. So here you can see the selected surfaces, we have a two reference planes, they are separated apart by the specified distance. This specified distance is given in the drawing. So the main difference between the flatness and parallelism is, in a flatness there is no datum required at all, there is no datum reference, but for parallelism we need a datum, like for which respect to what you need the datum plane. So the datum plane should be with respect to what. So thus the question will arise for the parallelism, whereas for flatness you will not have any datum plane at all. And it can be an axis whose entire length is at equal distance from a datum plane or a datum axis. So it may be a plane as well as for a axis also. So if it is applied, depending on the application, a parallelism tolerance may be cylindrical also and parallel to a datum plane. So for example, in this case, this is the datum axis, the whole center becomes the datum axis, and the second hole we are giving a tolerance zone of cylindrical tolerance zone of 0.003. What it is trying to say is, the whole center, the axis of this hole should be lying within a 0.003 cylindrical tolerance zone with respect to datum axis A. Again, it can be between two parallel planes that are parallel to a datum plane. So for our further understanding, we can refer to this feature also. Here you can see in this diagram, the datum plane is at the bottom. So this is the bottom feature, and they are trying to make sure that one more feature above, it should be parallel with respect to datum A at a wide tolerance zone of 0.010. So here you can see in the pink color we have created two reference planes which are separated by a distance of 0.01, and the control surface which we are going to test it out should be lying between these two planes with respect to the bottom plane. So bottom plane is A. The planes which we have selected, the two planes which we have selected for reference, should be parallel to the datum plane. In perpendicularity, the reference planes were perpendicular to the datum, whereas in parallelity, the reference planes will be parallel to the datum. So this is the similarity or clear understanding, you can get it. So in this case you can see here, so they are trying to control the whole axis, with respect to the face, of this particular component. So datum A is made as the face, and they are given a wide tolerance zone of 0.05. It should be parallel with respect to the datum face A, the whole axis. This whole axis, you can see the two parallel planes, they are separated by a distance of 0.05. The axis should be parallel to this particular face within a wide tolerance zone of 0.05. And as a rule, it need not have to be a 50% like in the form tolerances, but in orientation tolerances, it is associated with your position tolerance and the size tolerance, and it should be less than the features tolerance. So for example, if the whole feature is having like, say for example, this whole diameter is say 10 millimeter plus or minus 0.05, means the tolerance of your parallelity can be up to 0.05. If the whole size tolerance is given as 0.01, then again the tolerance of your parallelism should be within 0.01 only. In this example, we can see a cylindrical tolerance zone. So in this diagram, what we can say is this feature, the diameter 4 holes feature, should be parallel with respect to this datum A. So the axis of the whole feature diameter 4 should be parallel to whole axis of the datum A within a cylindrical tolerance zone of 0.003. So this is the cylinder they have created. This is the feature which we are going to control. The whole axis, the features axis, with respect to that axis, we have created a hole or a circle or a cylinder with a diameter of 0.003, and we need to make sure that the whole center of this axis, this whole axis, should be within this cylindrical tolerance zone. So your axis can be tilting within this cylindrical tolerance zone of 0.003 only with respect to the datum axis A. So now inspecting for parallelism. So how we are going to check the parallelism? So parallelism can be verified using a surface plate and a dial indicator. It is like similar to the perpendicularity checking only. So we can check straight away using a dial indicator and a surface plate itself. Directly you can place the component on the surface plate, and you can use the dial gauge to move over the surface and make sure that it is parallel to the controlled, like it is parallel to the datum reference. I'll show you a video so that you will understand in a clear manner. So here you can see this is the component which they are going to check for parallelism. So one face they are going to check with respect to the bottom face. So the bottom face needs to be rested, and the other face they will be checking for the deviation using a dial gauge. So it is clearly rested on the surface plate, and this dial gauge will be applied on the opposite face, and some pressure is applied, and they are making the dial gauge to 0, and it will be moved all over the surface and checked for the deflection in your dial gauge. And if the deflection in the dial gauge is coming within the tolerance specified in the drawing, then this component is accepted. You can see the deflection slightly here. So it's not showing too much, so within the tolerance zone, so this component will be accepted. Okay, this is the method. So now representation of parallelism in a drawing. So how we are going to represent parallelism in a drawing? So this is the feature control frame. Since it is a orientation tolerance, all the three zones are filled. So first zone we have the geometric characteristic symbol, that is two slanting line, and second zone you can have a tolerance zone shape also. It can be cylindrical or it can be wide tolerance zone. So if there is no diameter symbol is present, it is wide tolerance zones. If you have a diameter symbol, it is a cylindrical tolerance zone, and the tolerance zone size is also given, and you can apply tolerance modifier also. Since it is applied for the surface as well as for the feature, tolerance modifier can be applied, and you need the datum reference compulsorily, and for the datum reference also tolerance modifier can be applied. So how we are going to read this one is, The feature for which this feature control frame is attached should be parallel with respect to A when the datum feature A is at maximum material condition with a cylindrical tolerance zone of 0.005 when the feature is at maximum material condition. So this is the way how we are going to interpret from the drawing. Thank you.